Right, good afternoon, everybody. Glad to see all the faces and welcome back to Georgia Tech Manufacturing Institute's Lunch and Learn lecture series. My name is Dr. Khalidi Brown. I'm a senior research faculty and education workforce development director with GTMI. I'm excited to host this series and glad to see all of you enjoying the content. Please feel free to spread the word about our lecture series. We do have about 5 to 6 lectures per semester. Today is our third lecture. So what I want to do first here is just introduce GTMI, and I'll give the audience some brief instructions before I introduce the speaker for today. GTMI is one of 10 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing, research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment located on main campus for basic research, as well as facilities for applied research over in our advanced manufacturing pilot facility, or AMPF. GTMI's mission includes educational workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI's AMPF is the headquarters for a groundbreaking initiative called Georgia AI Manufacturing Technology Corridor, or Georgia AIM, funded by a recent federal EPA grant of $65 million. Georgia AIM is expected to profoundly impact Georgia and the nation's economy through the equitable development and deployment of talent and innovation in artificial intelligence for all manufacturing sectors. The AMPF currently has state-of-the-art equipment in metal, additive, and hybrid manufacturing, and is currently transforming into a demo facility for automated smart factories that incorporates IoT, AI, digital, and robotic manufacturing technology. GTMI hosts a lunch and learn series each semester. These sessions are excellent opportunities for Georgia Tech faculty, undergraduate, graduate level students, and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. Today is our third lecture of the spring semester, and we're both in-person and streaming via Zoom. We want these seminars to be interactive. So after I do my introduction and we start the seminar, we'd love for you to raise your hand, ask questions. If you're online, we have an online audience. You guys can put your questions in the chat, and the speaker will address them as soon as possible. All right, today I'm pleased to introduce Dr. Guha Manogharan, who will discuss hybrid additive manufacturing, role of AM in advancing traditional manufacturing methods. Dr. Guha Manogharan is an Emmert H. Bashore Faculty Development Associate Professor of Mechanical Engineering at the Pennsylvania State University Park. He is co-director for the Center of Innovation Materials Processing through Direct Digital Deposition, and also heads the System for Hybrid and Additive Processing Engineering, or the SHAPE lab. This lab focuses on additive and hybrid manufacturing with an emphasis on biomedical, defense, and aerospace applications. Dr. Manogharan received his PhD in 2014 and master's in 2009 from North Carolina State University. He has received the 2022 ASME Eclipse Award and several Young Investigators Awards, such as 2021 ASTM, 2020 NSF Career, 2018 Fame Junior, 2017 SME Outstanding Young Manufacturing Engineering Award, 2016 IISE Outstanding Young Investigator by Manufacturing Design. His work is supported by NSF, DOE, ONR, AFRL, and Manufacturing PA. All right, today's presentation, Dr. Manogharan will discuss recent advancements in AM and how AM can be seamlessly integrated with other manufacturing methods. For example, hybrid AM to address major challenges in 2 different application domains, such as industrial, including aerospace and defense, and orthopedics. All right, Dr. Manogharan.
Good afternoon, everybody. Thanks, Bill, for the introduction. Can everybody hear me okay? Thanks again, Tom and Caroline, for inviting and hosting me for it. So, you might wonder, what does Freeburg and Dragonfly rings and bridges and whitewater rafting have to do with manufacturing? I want to kind of give you a teaser for why and what gave some inspiration for some of the ideas related to manufacturing science questions that we are working on. So a brief introduction about Sim3D. So Sim3D is our Center for Innovation Materials Processing. It's Additive Manufacturing Research Center across 5 different colleges, 17 different departments. We have about 22 full-time staff and whole array of equipments and AM capabilities. So I just wanted to quickly highlight, predominantly in metals, but off late we have kind of consciously expanded into composite polymers and high temperature polymers. So these are some examples. So we have a wide range of metal powder bed, wire DED, instrumentation, and we have a couple of strategic partners like 3D Systems who have, so we have like two and a half staff engineers on site. So that's been very helpful in being able to access back and forth and so forth. So some examples of, again, these are not my projects, but I wanted to quickly highlight some of the well-known examples and topic areas that at Sim3D we work on, anti-counterfeiting, dissolvable support. So Sim3D is run with by College of Engineering and Applied Research Lab. Applied Research Lab is the UR, predominantly with TV. So that's pretty much Sim3D. So if you are in Penn State, please do let me know. I'll be more than happy to show off our Additive Manufacturing Center. And I want to talk about some of the topics that my lab is involved in. So I call ourselves the experimental, advanced manufacturing lab. We do use computational tools that exist. We build on it, but we collaborate a lot. So all across metal, mostly metals, but little bit more into ceramics these days, including the post-processing. And just a very quick broad stroke snapshot of some of the topic areas that are, that we have been active in the past few years. Is direct metal AM with an emphasis for biomedical implants, more on the polymer sides for AM orthotics. I don't have slides on it yet, but I'm working on a really cool project on embedded fluorescent particles to better model aneurysm and left ventricle, some more on the DLP side. I'm getting to learn a lot about the physics and chemistry of DLP. And mostly I'm going to talk today about, I was thinking of which topic to touch upon in this during this luncheon. And I wanted to pick a topic that's kind of out of the norm in terms of direct metal AM and data analytics and stuff. So I'm going to mostly talk about 3D sand printing and sand casting, and I'll briefly touch upon orthotics. We can pretend to be a design group. We are not a full-blown design group. We have collaborators who are excellent in design methods with whom we work. Some of our active funding agencies are to the right. So some examples of other projects that I thought the audience might be interested in that are currently active is we are trying to get a better handle on the stochastic nature of pores, particularly in binder jetting. So we're trying to eliminate or if not minimize the stochasticity of pores and actually engineer the pore networks that you can achieve by a combination of multi-material powder bed deposition or multimodal powder bed deposition. And 2 target applications that we are currently working on is hypersonic materials, where we are targeted infiltration of metal to get a metal matrix composites. And the one nice thing is we have our own custom built binder jet system. So that allows us to have collaborations with excellent colleagues, in this case, Dr. Adrian Van Duyn, who is an MD expert. So we are not constantly developing resin, constantly going through trial and error of curing and sintering profile. We also do quite a bit of post-processing, but I just wanted to highlight some topics that might be of interest here, is trying to understand, again, the pore roughness, but also looking at internal flow channels through abrasive flow machining. Just an example, trying to understand. So we have 2 aerospace projects that are looking at internal turbine components with the internal flow channel. How do you better characterize the surface morphology, and how thin can you print, and what can be the wall-to-wall thickness so you are not bending the shape. So more for like, fuel injector kind of application. So this is not a plug, so I won't very quickly go through it, but I do want to kind of give an example of, graduate research and lab and some of our education stuff. So we have a master's in additive manufacturing and design program, and reflecting the breadth of our center, the program is not housed within one department. So we have 5 different departments with engineering, science and mechanics on the laser powder, particle physics, design for AM topology optimization, process structure properties, and the IE course on economics. And I get to teach the hands-on metal AM lab. And you take all of these courses before you come to take this lab. And sticking to trying to make sure we are not just printing cookie cutters and trinkets. It has our metal AM project at the end, and every year it's a new flavor. Last one we did was rib, rib implants, and the one before that was oil and gas. But this was one of my favorite where you do, this is a grad course, so you will get a grade only if your engine runs. And if you need extra 6 weeks, you get deferred grades. But so this is just an example of, taking advantage of all the metal AM, and I let the students showcase this as a portfolio when they go out for internship and so forth. But this is just an example of having an hands-on metal AM lab that takes, gets a student to think about GD&T, what are the additional features. And one of the cool things, again, kudos to the student here. If you see, we just have the oil here, but he came up with a little own throttle example. And so this class project ended up becoming a full-blown project with the aerospace company and some of the heat exchangers design as well. So I would say the Metal AM lab course has been absolutely fantastic teaching that, because we were able to get a new flavor of project every year, oil and gas. And next year I'm planning to do one for micro nuclear reactors, e-pipes. So one of the cool things that we just got a funny, very exciting capabilities, and I haven't published this out yet. So these are from Fraunhofer, but this is from our lab. But I just wanted to give some examples. So we have a 3-powder multi-material deposition system with a voxel resolution between 150 to 300 micron. And this really opens up a lot of things with multi-material AM. So this is more like a teaser. Hopefully by this time next year, we have a little bit of more publications on these. But what I do want to highlight, and particularly to the researchers in the audience, if this is of interest to you or of value to you, please do reach out to me. Because what we are realizing very quickly is everything that we know from single material laser powder bed. And every length scale is quite different when you are doing multi-material laser powder bed, which is not the same as multi-material functionally graded, DED, directed energy deposition, because the combinations of materials, your mechanical, and then the melt-pool mixing, and you can see steel and steel mixing with the copper bronze in this case, and the mechanical properties is quite different. So I'm really excited about this, because it's really getting me to reimagine and gain new knowledge on computational materials, topology optimization. You cannot use just the same sensors either. But the emissivity is going to be quite different from material. The densities are going to be different. So how do you identify fracture sites? Can we use ultrasound? So then how does ultrasound NDT methods interface with multi-materials? So it's a wild west, to be honest, but it's quite exciting because we get to work on really cool fundamental research. But the nice thing about having applied research lab with Sim3D is we are always surrounded by colleagues who are always looking at applied aspects of all of this. But I wanted to give a quick snapshot on how this system works. Is I kind of think of this as taking a chessboard or a checkered board and you're wrapping it around a roller. And you're using negative pressure to hold on to the powder into this little pixels. And you synchronize the speed of your roller and your travel speed to selectively deposit material, and particularly based on your slice information. So all you need is the CLI information. So this is just PSU, and this student did an undergrad at University of Florida, as you can see from her color choices here. And she was pretty adamant about it. So I'm really kind of excited about it, because it's really making us kind of reimagine what we want to be doing in the lab in the next few years, which is quite different from what we have been doing, but also different from others, and also collaborate with colleagues who are working at different length scales. So one project right now is multi-material bone scaffold where zinc. And the next time you go to, I don't know if Irish Streeter is your local grocery store here, but it was in North Carolina. Next time you go to your local grocery store, take a walk down the supplement section. You will see a lot of magnesium and zinc supplements for bone growth. So they are biodegradable, but you don't want to make the whole thing out of zinc and magnesium, because you need to give mechanical strength. So we are looking at this multi-material powder bed system as a means to be able to grade bone scaffolds, as an example, or energy storage with solid state energy storage, or thermal fluidic surfaces where you can have high temperature strength like GR COP, but then you have very high thermal conductivity material on the other side. So it's quite interesting. So hopefully this time next year, I have a little bit more information on all of this. And I'm gonna kind of skip this slide because it's more about the facilities, but everything, all of this is with a single material. And we want to figure out how can we push the science beyond multi-material. So with that, I want to jump into the topic. So before we go into AM, I always start off by saying AM is a tool in your toolbox. It is not a magic, it's not a Swiss army of all manufacturing processes. And we have thought of always looking at AM based on your complexity, either of the material or the design, level of customization and production volume. So hopefully you're able to check one or, if not all three boxes. And I'm sure you're aware of all the examples. But you might wonder, what does AM to do with sand casting? How many of you have done laser powder beds? Direct metal printing. How many of you have done directed energy deposition? How many of you have done binder jetting? So binder jetting, the way the system works is I kind of think of it as like going to the beach and making sand casting. Except I'm not particularly artistic or dexterous. You're using an automated system to deposit your material, and you're depositing binder, and you can actually print sand. And you might wonder why we want to print sand. So fair warning, my original graduate training was not in foundry. It was on actually machining and direct metal printing. But I saw an opportunity for something that we can take from our design for manufacturing to kind of think about casting. So casting, again, I won't bore you with all of these details, but they say you're never 8 to 10 feet away from a casting in the US. Either it could be a car engine or it could be a valve behind this drywall, jewelry, cast parts in your laptop and so forth. So casting is everywhere. It is considered the oldest process, but I have a dear colleague at Charlotte who always argues grinding is the oldest process. So it's a toss-up between grinding versus casting. But my point is sand casting is everywhere. And I think sand casting constitutes 70% of the total casting, and everything that starts. I'm not going to go through your manufacturing processes course, but as a quick refresher, you might remember you have a cope and drag, you have a core for your hollow shape, and you pour liquid metal, and everybody would have seen this, right? In your manufacturing processes course, which was good. If you think about it, your metal pours, is first poured through the pouring basin, down the sprue, takes a turn to runner and fills. So there are typically 4 stages in casting: pouring, then you're filling the mold, then you're feeding the mold. So that's why you have risers, because they shrink. Then you finally have solidification. So all of this is good. And does anybody have an idea of how much it costs to directly print a metal part, let's say laser powder bed? Anybody have some dollar per cubic millimeter or cubic inch? Titanium, stainless steel. The last I checked, it was somewhere between $18 to $20 per cubic inch of printed Ti-6 before heat treatment. And the cost of printed sand mold with binder jetting is 10 cents per cubic inch. Even that does not compare oranges and apple when it comes to your mechanical properties and your microstructure. But the number of alloys that have been qualified for DoD applications through MMPDS, it's close to 200 cast alloys. A number of alloys that have been qualified for powder bed and DED, I think 6 or 8 the last I checked. But again, you would have seen all of this. That got me really thinking about, okay, is there anything in casting that additive manufacturing can do differently? And thankfully there was. How many of you have done skating, skateboards, rollerblades? How many of you have seen winter skiing competitions or winter Olympics? You would have seen those off pipes, right? So the liquid metal that first comes down the pouring basin into your sprue, and that first touches the sand, should get oxidized and will get oxidized. And ideally, you want it to be like your skating pipe. It stays like this nice pipe with a shell, and your clean metal, flows through and fills your cavity. But if you go down your pouring basin and you make a 90-degree turn, your potential energy to kinetic energy and your bend coefficient, what happens is you end up actually folding your oxides into your castings, like into your liquid metal, and you get a lot of gas trails and so forth. Then good news is the literature is full of evidences that says if you're over 0.5 meter per second when you enter the mold, you're going to have surface turbulence and you're going to have trapped air and you're going to fold these oxides into like little pancakes. Oxides, as you know, fatigue is not good. And that's why if you go back to your mechanical design courses, the factor of safety for casting, the first rule of thumb is do not use castings for fatigue applications. And if you're going to use it for anything, you have a safety factor for 3 to 5 minimum. The reason being lack of melt flow control and the literature across different alloys, whether it is aluminum, steel, iron, and so forth, and across different part geometries is full of parts that shows you have oxide films, you have cracks, you have bubble trails, and so forth. And it's in the actual complete casting handbook by the father of foundry science, as he is called, John Campbell from University of Birmingham in UK. It's a nice, real, yellow big book called Complete Casting Handbook, and it's in the 3rd page. Even under highly controlled condition, casting is a highly unpredictable process. And as engineers, particularly manufacturing engineers, that really drives you nuts. Even under highly controlled conditions, it's an highly uncontrollable process. So that got me thinking about, can we reimagine the design principles in sand castings? How many of you have filled ice cube trays and left it in your freezer? Yes. So if you look at the ice cube tray, you have this nice angle, right? So that your ice cube will pop off. But imagine now, you run a business that makes ice sculptures for parties, and instead of an ice cube tray, you can literally print your mold and then you pour liquid. So taking full advantage of digital process, right? And casting in particular is a notorious industry for tribal knowledge transfer. What I mean by that is you had grandfather was pattern maker, father was pattern maker, and it was one of those industries that I took some time driving around Pennsylvania, Ohio, New York, which was that belt, which has the most number of casting industry in the US. It's going to be the last industry to be most welcome for, adapting new technologies, unless you say that you're moving the ball 50 yards, you're improving something by 20%, not by 2%. So it got us thinking if binder jetting, 3D sand printing can be used somewhere to improve the casting process. So the way it works is you spread a layer of sand, which is traditionally used foundry silica sand, and you can put down binders. There are different types of binders. Furon is a commonly used one. So the good news is, if you are a casting or a foundry company, you are not introducing new material, new organic compounds that you are not already using. But that removes one barrier. There are different OEMs that are available, but again, we want to solve problems that are not tied to one particular OEM. Like for example, in this one, you're not spreading the entire layer of sand and you're just depositing for whatever mold you need. So we started with a very small America Makes project, kind of thinking of, can we take what we know from direct metal AM and apply it towards sand castings, whether it is consolidating parts. This is for a big automotive company in Michigan, or topology optimization for casting, which was quite new at that time. And we started looking into what is it that we can do to, first we started by looking into what can we do to the design of the part. Just like how you look at design of the direct printed part. But then we started thinking casting is full of challenges with defects, not because of the design of the casting, but because of the way the metal is introduced into the mold. And because the 2D drawing that you saw in every manufacturing textbook is the way casting has always been made, because that's the way tooling has been made. So we wanted to look into not improving just the part itself, but can we improve the casting performance? That is, can we introduce new concept that could improve the way the metal is being filled, and the metal is being fed into the mold. So what you see up in the top here is the traditional sand casting, and everything that you see in this little peach color, we are in Georgia, so it turns out nice coincidence, is both physical labor as well as tooling. Whether you make the physical mold, then you make the mold and so forth. But if you go to digital 3D sand printing, the only process that is physical is printing the mold, putting them together, and then just filling it. you can you do not have to invest in a tooling for every single mold. And this was really mind blowing for me. The first time I went to a foundry that was a DLA listed, they serve DOD. They had about probably this size of this building, or probably 75% of this building of tooling. Each of this tooling was not a joke, $25,000 to $40,000 each. They don't own the tooling. The big tier one DLA, the Boeing and Raytheons of the world owns those tooling, but it is housed in this foundry. And some of the toolings belongs to platforms that were started in 1980s, but they cannot destroy the tooling because it's a big chunk of material. They just do not know when they're going to need it. And then they are paying close to $25,000 a year, just keeping that building with the right humidity and nothing else. And they know that they're going to probably only cast 3 or 4 of those. They're not going to cast like 3,000 of them. So again, gives you a good example of where additive manufacturing can be used in a meaningful way from just an economic standpoint. So we'll go back to this drawing or this schematic and look at what are the most common culprits, right? The metal goes down the pouring basin, goes down the sprue and fills the riser. And then we started thinking ourselves, what is the best way that we can address this and make sure we are designing a geometry, and sprue in particular is the biggest culprit. And remember, I showed you in the very first slide, interstates. How many of you drive a car? I've driven a car. How many of you take exit off of the freeway? How many of you have seen a little warning that says tipping hazard? How many of you just jump off of the freeway at 90 degrees? That's exactly what we are doing to this liquid metal. It is going straight down from the top of your bridge, hitting a pit and then making a 90 degrees turn. First order differential, actually Department of Transportation has a requirement. If your first order differential of the exit is not a straight line, you need to put a tipping hazard. So that got us thinking, we can print sand mold that can make sure that the velocity, and also we can do the same thing with runners. It doesn't have to be straight, you have a lot more freedom, such that the metal, when it enters the mold, is at 0.5 meter per second or below. And it's not going to take a roundabout way that it's going to be cold. And we can make sure there are no abrupt section changes and give the constraint that it should still fit the same bounding volume of a traditional mold. Because we can now print sand molds, we thought theoretically the conical helix should be the best, from going from point A to another point B. That's the most gradual way of reducing velocity. But we also wanted to come up with a solution, going back to my visit to the tooling company, where they had this big patterns. Why does it all have to be straight? You could just print just the sprue part of it and use it with traditional standard 1D to 2 and 2.5D and a true 3D. And we started with, again, I won't go into the details, but I have backup slides with it. We wanted to attack the systematic modeling of these geometries such that it is independent of the alloy, independent of the corresponding pouring temperature, and it is independent of the size of the mold, size of the part. As long as you have the thermophysical properties of the weld and you know what is the amount of metal you need to pour, can we theoretically design such that we make sure that the liquid metal does not solidify before it enters the mold. So you might wonder why I have this 200 by 100 millimeter most exciting rectangle in casting, but it is the benchmark in casting. So if you go back all the way to 1970s and 80s, and everybody who comes up with a new CFD tool for filling solidification, they always compare it against this particular geometry. So think of this as the NIST benchmark, but for casting in particular, because there are some guidelines on where to take bending samples and so forth. So what's happening here is, I think if I was right, this was CB7, which is like equal to 17.4 pH steel. You're pouring liquid metal, it's going down the mold and filling your cavity. And anything that is red or above is 0.5 meter per second. The bad news is you can see this little streak of red, which means it's at more than 0.5 meters per second. But the good news is it is extremely consistent with what has already been reported. And in particular, one really interesting study from 1996 and 2001, where they actually put, and one was from University of Wisconsin and one from Poland, they put a sand mold inside X-ray, and then they poured liquid metal, aluminum 390, and then they took as many images as they can. And you can still see the same fountaining. I did not want to go to my facility spoke and try to do that. So I thought I'll just do the simulation and then, collaborate elsewhere with foundries to do the actual, to do some of them. So from our mathematically designed parabolic, you can see there is still a little bit of a streak there. And this is our conical helix for all of the same alloys, same pouring conditions and so forth. And you can see that you don't really have a big, streak of red. So you're not violating any surface velocity. All of this is good. Computations or computation, you just need to evaluate it. So we were purposeful in the way we were designing those experiments such that you can either print the whole mold or you can just print the sprue. And then so made sure our design of experiments add this mixed model, so that our approach is independent of whether you're printing the mold or printing only the sprue with or without vertical split versus horizontal split, and also because of the difference in mold constant. Whether you're using green mold, no bake mold, or whether you're using ceramic silica, we wanted to come up with something that could not be put only within one particular alloy or one particular method. So we did this, and we did this for a whole bunch of alloys, and we did castings for a wide range of alloys. And when my student first showed this, I actually thought there was some error in our CT data. So this is from the straight sprue, this is from the parabolic, and this is our conical helix. So what you're looking at is reconstruction of micro CT. If I remember it correctly, the voxel size was 15 or 17.5 micron. And good news, the straight sprue, you can see this nice center line shrinkage. Parabolic, you saw this little one fountain and the conical helix looked too good to be true. So I want to make sure that we are being very clear about it. So we got the plate, we sent it to three different service bureaus for micro-CT. And we also shared our raw data with a couple of others for them to do segmentation all by themselves. And the green is state of the art at that point, which was straight sprue. The red is the parabolic, and you can almost see no helical. We actually found a 99% reduction in defects with statistical significance for CB7. And our hypothesis is because we are reducing the velocity that we were able to do that. But again, micro-CT is slightly better than CFD only results, but you still need ground truth results. So we did 3-point bending test again and again with and without filters as well, to see what was the evidence. And with statistical significance for steel, we found 14.7% increase in flexural strength. And in the case of aluminum, I think I might have a slide on here. So we repeated this again for aluminum and also for cast iron. In the case of aluminum, we found a 24.8% increase in strength, and then cast iron, this number might look too big, 46%. But cast iron is not as sensitive to oxides anyways, but we were more interested in aluminum. So I don't have all of this is published work, but I don't have one project that I'm currently wrapping up for ONR, nickel aluminum bronze. It's an alloy of big interest to Navy because it has high strength, but also very good corrosion resistance. But it is a pain in the neck material to weld because you get a lot of macro alloy segregations. But what we found was we not only increased the mechanical strength through our 3D sandpaper, most particularly for really large naval components, we found that our way of mixing, unintended consequence of the way the metal was filling the mold, we ended up getting a lot more homogeneous alloy segregation. So we have those samples right now in somewhere in Caribbean for corrosion testing. So I'm really looking forward to this. So we also did some other work on the design methodology, on how do we now redesign just the casting itself. I would say this is too much on the applied side to my liking. So this was some of my early work there. But the good news is industry are using it actually. I've had four graduate and 3 undergrad students from my lab going and spending a semester and a summer, 9 months or so with different foundries, actual knowledge of transfer, and they've all been very kind with being able to pour materials on alloys that I cannot pour on campus. So it kind of win-win. There is one example of the Alcoa bearing part that we did. I think we did n equal to 5 for this. I think on average, we showed that we can reduce for casting, sand casting without heat treatment. You can increase mechanical properties by 50% with volume and weight, but increases, safety factor as well. So some ongoing work, I think I have a little bit more updates on this is we wanted to then, we want to now able to see through it. We cannot obviously see through the mold. So we are trying to work with colleagues who are developing some metal analogous liquid at room temperature. So that has the same Weber and Freud's number at a particular Reynolds number that it behaves like aluminum or steel. So we want to be able to do 3D printed molds, which is easy to do with clear plastic to verify our hypothesis that, it's because of the reduction, which I think at this point we are comfortable making that claim. But I would still like to see that, to be able to see it with high resolution and high speed camera. And this is a really cool education tool as well. So that's part of the fun as well. So for example, in this one, we have had a newer versions of this with where you can, instead of just regular liquid, I have a student on undergraduate honor student mixing different cornstarch with sprinkles in them. And then so he's kind of like simulating inoculants in casting. And instead of just regular water, what if you just pour bubbles? So kind of using this as a tool to use your smartphone to be able to do, track the, the track the liquid metal, and using this more as an educational tool as well. So this has been a lot of fun. So we are going to get a big workforce development grant for casting education, similar to University of Tennessee has a big machining program called ACE. So we are going to lead one on casting. And I'm working with Penn State Legal to make sure if this is allowed or not. I want to make a student competition where they machine the high school logo or middle school logo out of food grade acrylic, and then they pour chocolate into it. And then they make candies out of it. But then learn the concept of pouring, filling, feeding, and use your smartphone. So learn image analysis, be able to do statistical analysis, some basic Python, simple CFD with open form and so forth. So I'm really excited about that. So before I switch gears, any questions? I want to make sure I give you all a breather and myself a breather. Any questions on this topic before? I know we have about like 20 minutes or less. I'll probably jump through some of these slides. If there are no questions, it means it was really, really good or really, really bad. I don't know which of these two have I. So if you have any questions about the sand casting aspects, I'm happy to answer, or we can switch gears to, go ahead.
So not being a casting person myself, the new geometry that you have to enhance the flow, right? To kind of slow it down.
Yeah.
If your mold is large and complex, does it also mean that it cools down too much if it gets into more complex sections of the mold? How does that, I guess there's an interplay, right? Between the speed as well as how quickly it cools, and then the viscosity changes as it cools and.
Absolutely. So the answer is yes, but it doesn't apply just to our conic, it applies to any sprue design. So the idea is the way we have written the algorithm is we are assuming whether it is straight or conical helix, you're going to have the same amount of superheat. The alloy is going to have the same surface tension and so forth, and they both are going to have mold wash and stuff. So the constraints that we have is the temperature and the velocity of the metal that enters the mold at this point should be the same. So like for example, in this particular case, so we have these different sprues that are not attached to the regular mold, so it's still away from it. And there are some examples that I cannot show, but I can roughly talk about it. This is a fairly simple geometry, right? There are some impeller parts that add much thinner cross sections where this conical helix, we had to be a little more creative and not have it all go in one direction, but this conical helix actually go around the geometry. So the heat of the metal that's going to be left in the sprue would still make sure that you're going to fill the entire mold and it's going to solidify uniformly. So think of like a donut impeller, but then your sprue is actually transversing the entire cross section, and it's going to continue to cool down. So you're not going to feed from the middle; you're feeding from the outside. Good.
You were showing the micro CT data with the defects. What are the common types of defects, casting defects?
Oh, everything and anything in the sense that you will get trapped sand, you will get oxide films, you will get gas pores. You can even get shrink, I mean, you'll definitely get shrinkage associated porosity. So what I say is, you would avoid the first in, first out. Whereas in sand casting, there is no first in, first out. There is first in and it stays in. And it absolutely stays in. The one saving grace with casting when compared to direct metal, and I make sure I put this in the first page of the proposal when about surface roughness, you cannot compare this with resolution with direct metal parts. And you cannot compare this with surface roughness of polishing either. I'm going to make an assumption that it's a sand cast part. You're going to get cast surface. You're going to remove at least 1/8 of an inch from the surface. So as long as I'm pushing my defects away to the surface, I'm kind of okay with it. So internally, oxides, trap gas, trap sand. And sometimes if you're using filters, I didn't show those. If you're using filters in your gate, sometimes if your filters don't have high temperature strength, some of them could end up getting broken up and it will be a nice big ceramic in the middle of a metal.
And then how does that conical shape help reduce the amount of defects?
So the way the conical, so what we are basically doing here is we are throttling the velocity of the metal exactly when it enters the mold. So but making sure that the metal is at the same temperature as it would be if it was otherwise. So I'll go back to the ice cube tray example, right? Instead of the ice cube tray just being here, now you can print a complex ice cube tray and you just pour metal, because bind rigid gets a bad rap that it's not strong enough like a direct metal, direct printed metal. But in the case of sand, it's actually good that it is not strong enough. It just needs to have enough strength that you can transport the mold from your printer to where you're going to pour,
Right.
but it shouldn't be too strong that after you pour, you cannot break it.
Right.
So hope that that answers. Yeah, go ahead.
Yeah, by slowing down the inflow, do you increase the process time from the animation? It basically fails twice.
Yes, that's a really good question. So yes, so we are taking longer to fill, but pouring and filling is only first two of the remaining two steps. Then you're still gonna have substantially longer time feeding the material, much longer time for it to cool down to temperature where you can have the shakeouts.
The process time is not significant.
Process time is not, if anything, printed sand mold is much faster to make the mold than to make a pattern and then go to tooling. But I'll go back to the even though that's like a 10-year-old plot of complexity, customization, production volume, that same thing applies here in sand casting as well. You cannot use this to make every single engine block that you're going to need in your car. This for special series where you can use these methods to make those molds. Any additional questions on this topic? I want to make sure, because the next one is going to be very different, and go ahead.
In terms of practical application point of view, so what's the quantitative comparison between the molds using this method versus traditional casting?
I would say from our own experience, when you say quantitative comparison, the cost is definitely a lot more comparable than you would compare direct metal parts with a forged or machining part, because the tooling that is required to make the molds, I mean, you'll come up with your pattern and your split plates, but then you have there are different V process, downscope process, and so forth. But the cost of making the molds makes economical sense if you're going to make like 300 to at least 500 of them. In that case, you don't want to be printing 300 of these. But if you need to have castings that are for DOD or DOE, really large castings that you want to make sure you're absolutely successful the first time, this is a pretty good process. In fact, I think I read somewhere actually in the World Foundry report, 35% of castings have some kind of defects, hand castings, and 87% of them are because of either design and or the process control when it comes to filling and feeding. So there is a new DOE program that's starting under advanced manufacturing where they sponsored a program to make 3D sand printers that are mobile. So it's big gantry-based sand molds that can be printed by the gantry-based sand printers. That could be in a ship or that could be transported in a train. So you're just taking them to the site of your installation, printing molds there and pouring metal and, filling it there. So I would particularly say that I found this as a nice gap that I think often we are overlooking casting as a process which could also benefit from additive manufacturing. And I think we have to end at 1:30, right?
Yes, sir.
So I'll probably skip through some of the slides of the remaining of the I would say the last 1/3 of the talk, because a lot of this work was done by former lab mates or lab students, and I won't go through all of them. But the idea is to use metal AM for biomedical applications, particularly for fracture and bone growth and so forth. So if it's okay, I would like to make sure I touch upon some of the topics that might be of highest interest and some of the newer directions that we are going. So the idea is, again, looking at it from either as a mechanical engineer or industrial engineer or a biomedical engineer, right? You're looking at going back to additive and looking at what is the equivalent of GD&T, ultimate tensile strength and your hardness that you see for metal, but for biomedical implants. So that's the way I looked at it. So in this case, it was more about properties, but not just any random property like compression or hardness, but looking at properties that were very specific to a particular anatomy site, whether you're trying to replace a femur or whether you're trying to replace a humerus fracture and so forth. So this is still a work in progress, but I think we have made some progress here in terms of your design space between your AM-enabled lattice structures, these are like AAA minimal surfaces, and your lattice sheet thickness and the size, because every part of your body prefers a different micron when it comes to your surface roughness or surface topology, pore size, and mechanical strength, Wolff's law, right? So you don't. So it's like going to the gym and working out. You build up muscle when you're straining that muscle. Similarly, for bone, there is something called Wolff's law, which is you need to have micro motion, micro strain at the interface between your implant and your bone. So that micro strain is going to create a response from osteons, which basically grows. It's like just like going to the gym and so forth. So this again, so we tried to figure out, can we design structures that are similar to the cortical bone, which is your outside, thick solid bones, and then your spongy bones, and there is a wide range. So since this work, we have some publications that are coming along the way that's going to be published soon, where you can grade from one thickness to the other thickness of different shape. So could you have the same DAC of a 3-point bending that you see in a femur bone and so forth? So the idea is, again, this was the motivation for that work, because you can see some geometries provide pore sizes that are much closer to your spongy bone, which is your peach ear, and some geometries that are much closer to your cortical bones with respect to your mechanical properties. So this was all work done by Mariam Tilton, who is now at UT Austin. And this actually has led to a little bit more interest from a couple of biomedical companies who have since given us some contracts to work on coming up with rib implants. So particularly in athletes or crashed victims and so forth, when they have rib fracture and actually rib, what they do is they end up taking a piece of their tibia, which is right behind your foot, and then they use it in your rib, because the profile and the properties and the local flexural properties match that of your rib, particularly that are around your lungs, which is a big problem, because for the rest of the life, then that patient is going to have a less than ideal quality of life, because they cannot apply the same amount of load in biomechanical applications. So we are working on a project inspired by this on developing rib implants that matches the profile, but it also matches the local slope of and deflection as well. Because we have found that different types of AM geometries, respond differently for your mechanical strength applications, this is a really, really good paper from years ago, but it's still one of the landmark papers that talks about how different sections of your bone behaves differently from an engineering standpoint, whether it is working as a viscoelastic material or whether you are having straight up crack like a ceramic composites or a crack deflection and so forth. So we are finding some really good similar trend here as well. I'm sorry for jumping across slides. I want to make sure I end with a topic that goes back to the multi-material. And you remember I had a picture about the tree bark and the dragonfly. So we are looking at some really exciting projects. Some I can talk about, some I cannot. For example, this is printed zinc, where we are trying to grade both the material assignment at the particular local site and the design that could affect your surface morphology, surface fluidic applications or biomechanical applications, but also be able to do it in pure 3D. So I'll probably, so we are doing some project with, with engineered surface textures in zinc. And I want to make sure we have additional time for questions. So I'm going to jump to the most important slide of all. To the people who make me look good, my students. So I want to make sure we have at least 10 minutes. So I won't go too much into the orthopedic stuff. I'll be around until 2:15. I don't think I have a meeting until 2:15. So I'll stay here for those who came for the orthopedics aspects of the proposal. I will definitely talk to you about it. So again, all the credits to collaborators and students in the lab and sponsors who, particularly students, they do all the artwork. So I know it's kind of an abrupt end without getting too much into the orthopedics. I apologize for it, but I'm happy to answer any questions.
One quick question.
Sure.
About the surface texture, the design space is so large. How do you navigate? What tool do you use?
About the surface texture, I'm glad you asked that, because we have been working on a newer, even though this was motivated by a need for a surface finishing project that was looking at how do we finish the surface. But what we have done is, this is from my backup slide. So we have developed a tool that could do automated labeling that is specifically trained for AM surfaces, regardless of build orientation. So we are looking at quantifying for any AM surface, how much of satellite powders do you have, and are the powders on top of the contours, and how much of polished surfaces you have. And so what we can do is we can take any surface and break it down into different masks and quantify which percentage of it is trapped powder, partially sintered powder, versus which percentage of it is and we can literally track them. In this particular case, we use this for surface finishing operation. So we were looking at how different orientations behaved when it comes to responding to for surface finishing. The idea is, if you have a part that has like a knee implant that is going to have surface polishing, you know what percentage of your surface falls under, let me see. So you know for different surfaces, you know what percentage of your part falls under top surface versus side versus curvilinear surface. So then you can recommend what could be the surface finish that could help you figure out what's your end target. So but the goal of developing the tool is not necessarily, it's not limited only to surface finishing or only to this particular type of surface finish. It's to be able to quantify the surface topology and see if we can come up with statistical representative of surface. I know some of my colleagues who are very much interested in the modeling of surface particle interactions, and they always ask what is the ideal AM surface we should use in their model. The idea is to be able to quantify it to get a statistical representation.
Thank you.
I was wondering back to the casting, was there a special consideration for minimizing defects from the binder jet process of the mold propagating into the cast, or was that not really a concern?
That's a really good question. Actually, excellent question. No, that was not a big concern because we were using the same sand that is otherwise used. We are using the same binder that was otherwise used. The only concern that was a lot of industry consortium funded project that I was somewhat involved, but it was too applied, is basically doing loss on ignition test and doing high temperature flexural strength to make sure it can withstand the same strength as it was regular mold. American Foundry Society funded a lot of that, but it was not a concern. Where I think it could become a concern is now there is a moving for using ceramic silica to address some of the silicosis problem, but still I think it's a very solvable problem.
Gotcha, thank you.
Any other questions?
All right, well, let's thank our speaker one more time.
Thank you all.
I want to encourage everybody to please come back next week. We will have Dr. Hua Zing, who's a senior director over at Micron Atlanta. He's gonna have a couple of his colleagues here. We'll have a few speakers from Micron present next week. So it's March 4th. And we'll also have a seminar on March 11th. So we're keeping it rolling. Thank you guys for attending.